In this lesson, we're going to cover infinite series, geometric and harmonic, nth partial sum, and then also a test for divergence. For our first definition, it says, if we add the terms of an infinite sequence, which is a list of numbers, in the form a sub n, starting with n equals 1 to infinity, we get an expression of the form a sub 1 plus a sub 2 plus a sub 3, ... plus a sub n, which is called an infinite series and is denoted by, we have sigma notation n equals 1 to infinity of a sub n, or it's just sigma of a sub n. So the thing to note for a series is you're taking the list of values and you're adding them up. For this definition, it says given a series, and we have sigma, we have I equals 1, and then you go to infinity. So you start by plugging in 1 for I, then you plug in 2, then 3. Because of sigma, you then add them up. Then it says let S sub n denote its nth partial sum. So you take that number and you plug it in, then you plug in the next value. So here we have 1, then 2, then 3. And then this number on the top tells you when to stop plugging in. So if this said I equals 1 to 5, you would plug in 1, then 2, then 3, then 4, and then you'd stop by plugging in 5. Then it says if the sequence S sub n is convergent and the limit as n goes to infinity of S sub n equals S exists as a real number, then the series, sigma a sub n, is called convergent, and we write it a sub 1 plus a sub 2 plus ... plus a sub n equals S, or your sigma notation, and it equals S. The number S is the sum of the series. If the sum does not exist, then we say that the series is divergent. This example says find the sum of the series, and we have sigma n equals 1 to infinity of a sub n, whose partial sum is given. So here's the formula for the partial sum. We have S sub n equals 2n over 3n plus 5. So S sub n is the partial sum for this series. So we start by plugging in 1 for n, then we add and plug in 2 for n, and then we add and plug in 3 for n, all the way until a sub n, and we're given that this partial sum, a1 plus a2 plus a3 ... plus a sub n equals this formula right here. So again, I just wrote it out so that we can see our partial sum. So next we can say that the sum of the series is going to be the limit of the sequence. So I'm taking this series and we're going to set it equal to the limit of the sequence. So the limit as n goes to infinity of S sub n is equal to the limit as n goes to infinity of our formula 2n over 3n plus 5. Next, to evaluate this infinite limit, we're going to divide the top and bottom by the highest power in the denominator. So we're looking at this variable right here, and we're going to times by 1 over n and 1 over n. So on top, when we multiply these, we just get 2. In the denominator, we're going to take this 1 over n, distribute to both of these terms. So we get the limit as n goes to infinity of 2 over 3 plus 5 over n. So at this point, we're taking the limit of the top and the limit of the bottom. When we take the limit of the top, we just get 2. When we take the limit of the bottom, we're going to do the limit of 3, which is 3. And then the limit of this term right here, as n gets larger and larger, this term is going to go to 0. So we end up getting that the sum of the series with this partial sum is going to be 2/3. Our next definition is for a geometric series. We have sigma, then n equals 1 to infinity of ar to the n minus 1. A is your first term, and then r is the number that you're timesing by every time. So you can see it goes a, then a times r, then a times r squared. The r value is being raised to the power n minus 1 in this case. Once you identify r, you're going to take the absolute value of it and check if it's less than 1. If it is, the geometric series is convergent, and it has the sum a1 over 1 minus r. And again, this sum occurs when the absolute value of r is less than 1. If the absolute value of r is greater or equal to 1, then the geometric series is divergent. This theorem says if the series, and we have our sigma notation of a sub n, is convergent, if that's the case, then we can conclude that the limit as n goes to infinity of the terms a sub n equals 0. And here we have a note. It says the converse of the above theorem is not true in general. So if you have the limit as n goes to infinity of a sub n equals 0, then the original series may or may not be convergent. Next, we have the definition of a harmonic series. So the form of the harmonic series is specifically 1 over n. So when you plug in 1 for n, you get 1. When you plug in 2, you get 1/2. When you plug in 3, 1/3. And then you're adding these up. So again, anything of this form is called a harmonic series. And you'll notice that the limit of the terms equals 0. But if you take the limit as n goes to infinity of sigma, starting at 1 to n of 1 over n, this will go to infinity. So therefore, the harmonic series is divergent. So I wanted to point out, let's say you have a problem where it's 4 over n, for example. You can always pull the 4 to the front, and then you would have sigma of 1 over n. And again, by harmonic series, this will diverge, so timesing by 4 will also diverge. Next, we have the test for divergence. If the limit as n goes to infinity of a sub n does not exist, or if the limit as n goes to infinity of a sub n doesn't equal 0, then we say that the series is divergent. This theorem says if we have sigma of a sub n and sigma of b sub n are convergent series, then so are the series where we have a constant in front of a, and again it says c is a constant, or if you take the sum of a and b or the difference of a and b, all three of these will be convergent. And we have it written out here. The first one says if we have sigma of c times a sub n, you can pull the c to the front, and then you have sigma of a sub n. So if this is convergent, then this series times by c will also be convergent. And then another property is if you have sigma of a sub n plus or minus b sub n, then you can rewrite it as sigma of a sub n plus or minus sigma of b sub n. This example says use the test for divergence to determine whether the series is convergent or divergent. If divergent, explain why. So we have sigma, and we have n equals 1 to infinity, and then we have 2n squared minus 1 all over n squared plus 1. So for the test for divergence, the first thing we want to do is we want to take the limit as n goes to infinity of the formula. So we have the limit as n goes to infinity of the formula 2n squared minus 1 all over n squared plus 1. To evaluate this infinite limit, we're going to divide the top and bottom by the highest power in the denominator. So next step, we're going to take this 1 over n squared, distribute it on top and also in the denominator. And then finally, we're going to take the limit of the top and the limit of the bottom. When we take the limit of the top, we get 2 minus. As n gets larger and larger, this term is going to go to 0. When we take the limit of the bottom, the limit of 1 is 1. Then the limit as n gets larger and larger of this term will go to 0. So this simplifies to positive 2. And I wrote it out since the limit as n goes to infinity of 2n squared minus 1 over n squared plus 1 equals 2, which doesn't equal 0. By the test for divergence, this series is divergent. And I want to point out one more thing for the test for divergence. If the limit of a sub n does not exist, or if the limit of a sub n doesn't equal 0, like in our last problem where it equaled 2, and that's obviously not 0, then you can conclude that the series is divergent. What I wanted to point out is that it doesn't say anything about convergence. So if you work out your problem and you get that the limit of a sub n equals 0, you can't conclude that the series is convergent. You would have to use some other process. And again, it just doesn't show us anything about being convergent. So that's just something to make sure to pay attention to when you're working out problems. This example says, show that the series, and the formula is 1 over n times the quantity n plus 1, is convergent, and find its sum. So the first thing I want to do is I want to look at S sub n. We're going to start by plugging in 1, and then plug in 2, and so on. So when you plug in 1, you get 1 over 1 times 2. When you plug in 2 for n, you get 1 over 2 times 3. When you plug in 3 for n, you get 1 over 3 times 4. So written out in this form, it's kind of hard to tell what's happening with our series. So what we're going to do is we're going to take this formula and we're going to break it down using partial fraction decomposition. So we're going to take this expression and we're going to break up the denominator. So we have n and n plus 1. They're both of linear form, so we're going to do a and then b in their numerators. Next, we multiply both sides of the equation by the expression n times n plus 1. So over here we get 1. On this side, we're going to get a times the quantity n plus 1. So you get an plus a, and then we multiply b times n. So we have 1 equals an plus a plus bn. Next, we take the an plus bn, and because there's no n term over here, we're going to set a plus b equal to 0. And then the constant a, we set it equal to the constant over here, 1. And since we have that a is equal to 1, we can plug that in right here, and we get that b is equal to negative 1. So we take our original sigma, and instead of 1 over n times the quantity n plus 1, we're going to put this expression where a is 1 and b is negative 1. So now what we're going to do is we're going to plug in 1, then plug in 2, and then plug in 3 and see what we get. So when I took 1 and plugged it in here and here for n, I get 1 minus 1/2. When I plug in 2 here and here, I get 1/2 minus 1/3. When we plug in 3 for n, you get 1/3 minus 1/4, and so on. I put the 1, the 2, the 3, the 4 up top so you could see what we were plugging in each time. Next, you can see that these 1/2s are going to cancel. These 1/3s are going to cancel. The 1/4 will cancel. And I'm going to stop right there. So what's left is you have 1, and then you also have this term over here. So what I want to do is I want to write this term with regards to n. The n that was being plugged in right here was 4, and to get from 4 to 5, the algebraic expression would be 1 over n plus 1. So let me go through that again. This is the n value. So n is 1, n is 2, n is 3, n is 4. And we're taking 1 and plugging it into the formula to get these terms. We took this n of 2, we plugged it in the formula to get these terms. Same thing here and here. So when we simplify this, you can see the 1/2s cancel, the 1/3s cancel, the 1/4s cancel. If we stop here, you're left with 1, and then you're left with this term over here. Mathematically, this 1 will always be a 1, so that's why I just dropped it down as the value 1. But as we keep going, right here this definitely says -1/5, but if we would have gone a little bit further, it would have been a different value. So that's why we want to represent it as an algebraic expression. And again, this expression corresponds to the number that we were plugging in here. So because this was a 4, and the n value of 4 is related to this number 5 as n plus 1, this is the algebraic expression that describes this value right here. By writing it this way, this works for any future expression. So like if we would have gone n equals 5, we would have gotten 1/5 minus 1/6. And this algebraic expression will still represent the fact that the 1/5 would have canceled and we would have been left with a minus 1/6. For the next part of the problem, it says, consider the limit of partial sums. So what we did is we took this series and we wrote it as the nth partial sum. And so to evaluate what this equals, we're going to take the limit of it. And again, this part of the problem is similar to one of the previous problems we did on the front page of the notes. So we're taking the limit as n goes to infinity of the partial sum. So that's going to be the limit of 1 minus 1 over n plus 1. To evaluate this limit, we're doing the limit of 1, which is just 1, and the limit of this expression right here as n gets larger and larger. This is going to go to 0. So we get 1 minus 0, or just 1. And since we got the value 1, we then say that the series is convergent, and the original series is equal to that same value 1. I have a note written out here. It says the above series, this one right here, is called a telescoping sum, where the sum collapses due to cancellations. So again, this series was rewritten like this, and then when we plugged in 1, then 2, and then 3, we wrote out all of the terms, and you can see that the terms canceled out. When that happens, it's called a telescoping sum. And then right here it says the diagram on the right shows the graphs of the sequence of the terms a sub n, which is 1 over n times the quantity n plus 1. So you can see that the terms for a sub n, as n gets larger and larger, the terms are getting closer and closer to 0. And the sequence s sub n of partial sums. So when we're taking these terms and we're adding them up, you can see the sum is plotted right here, and it's in the notation of s sub n. And you can see the partial sums. The sum is approaching a height of 1. So it says, notice that a sub n goes to 0, so the individual terms go to 0, while the sum of the terms is going to 1. So again, this is just to demonstrate the difference between the terms versus the sum of the terms. This example says, determine whether the geometric series is convergent or divergent. If it is convergent, find the sum. So for part A, we have 1/8 minus 1/4 plus 1/2 minus 1 plus ... So for a geometric series, the first thing we want to identify is our common ratio, or R. So R is the number that we're multiplying by to get from one term to the next. So sometimes you can just look at your series and you can go, oh yeah, from 1/8 to -1/4, you're multiplying by whatever the number is. If that's ever challenging to identify, you can always solve for R, and the way you do that is you take one term and you divide by the term before it. So we're going to go -1/4, and then we're going to divide by the term before it, which is 1/8. So we get -1/4 times 8. So you end up getting -2 for R. So once you identify R, then you take the absolute value of it, and then here we're getting +2. And then I'm going to go back to the definition on the front page. So you check your absolute value of R. If it's less than 1, the series is convergent, and you use this formula to find the sum. If the absolute value of R is greater or equal to 1, then the series is divergent. So here we have the absolute value of R is equal to +2, and that's greater or equal to 1. Therefore, the series is divergent. For part B, we have the series 1 plus 0.4 plus 0.16 plus 0.064. And then you can see that to get from 1 to 0.4 and from 0.4 to 0.16, our R value is 0.4. So now we're going to take the absolute value of R, and that's just 0.4, and 0.4 is less than 1. So since our value is less than 1, the series is convergent. So now we're going to find the sum, and to find the sum we use the formula A1 over 1 minus R. So a1 is the first term in the series, so a1 is 1. And then in the denominator, we go 1 minus r. So that simplifies to 1 over 0.6. 0.6 is the same as 6/10, so that's going to be 1 times 10/6, or 5/3. So this is the sum of this geometric series. For part C, we have sigma n starts at 1, goes to infinity. We have -6 to the n minus 1 over 5 to the n minus 1. Since both of these have the same power, what we're going to do is rewrite this series. So instead of both of them separate to the power of n minus 1, I rewrote it as -6 over 5 all raised to the n minus 1. And now you can identify r. R is the number that's being raised to the variable exponent. All right, so now we're going to take the absolute value of r. So the absolute value of -6/5 gives you +6/5, and that value is greater or equal to 1. Therefore, the series is divergent. This example says, what is the sum of the series? So we have pi over e squared minus pi over e cubed plus pi over e to the 4th, and so on. So you can see to get from one term to the next, we're multiplying by -1 over e. So this is a geometric series. And I wrote that out, a geometric series where r is equal to -1 over e. Just a little tip, anytime in AP Calc that it's asking you to actually find the sum of the series, that means it's going to be a geometric series and that it's convergent, and you're using the formula a1 over 1 minus r. So that's going to be a nice little hint. Okay, so let's actually do the problem. We're going to first take the absolute value of r, and when you do that, you get +1 over e. Remember, e is approximately 2.718, so 1 divided by 2.718 is going to be less than 1. So therefore, the series is convergent. To find the sum, we're using that formula a1 over 1 minus r, where a1 is the first term of the series. And make sure when you're plugging in r, it's the actual value of r, not the absolute value of it. So we're plugging in -1 over e for r. In the denominator, the negative becomes a positive. We want to combine this to one fraction, so the common denominator is going to be e. So I'm going to times this 1 by e over e. So we have e over e plus 1 over e is going to make e plus 1 over e. And then next, to simplify this, we're going to copy dot flip or multiply by the reciprocal of this fraction. And here you can see that this e is going to cancel with one of these e's. So we get pi over e times the quantity e plus 1. So our final answer is D. This example says determine whether the series is convergent or divergent by expressing the nth partial sum, s of n, as a telescoping sum. If it's convergent, find its sum. And we have sigma n equals 1 to infinity of 2 over the quantity n squared plus 4n plus 3. So the first step is, since the denominator factors, we're going to rewrite this fraction using partial fraction decomposition. So we have 2 over the quantity n plus 1 times n plus 3. So we split it up like this. Now we're going to multiply the entire equation by the quantity n plus 1 times n plus 3. So on the left side, you just have 2. On the right side, we're going to multiply a times n plus 3. So you get an plus 3a. Then we multiply b by n plus 1. So we have bn plus b. We have an and bn. So we're going to take a plus b, and because there's no n's over here, we're going to set that equal to 0. And then we take the constant values 3a plus b, and we set it equal to the constant over here of 2. To solve this system of equations, I'm going to multiply the top equation by -1. So you end up getting -a minus b equals 0. I just copied down the bottom equation, 3a plus b equals 2. So now when we add going down, the b's cancel. We get 2a equals 2. So a equals 1. And since a is 1, we can plug it in right here, and that means b is -1. So now that we have a and b, we're going to plug them in here and here, and then we're going to rewrite our series. So now we'll write out the series. We're going to plug in 1 for n, then we'll plug in 2 for n, and then 3 for n, and so on. So I got them all plugged in. So now at this point, I want to see which ones cancel out. So this -1/4 cancels with this 1/4. This -1/5 cancels with this 1/5. This -1/6 cancels with this 1/6. And I'm going to stop right there. So you can see the values in the front that are left. You have 1/2. You also have 1/3. And even if we were to continue taking this out, you would still have the 1/2 and the 1/3. Those will never change. But what I wanted to point out is if we plugged in 6, then you'll have some more terms cancel out. So again, that's going to play a factor into what we write next. So when you look over here, we have -1/7 and -1/8, and we want to write them algebraically. So right here we have n equals 5, but this fraction says -1/8. N equals 5, but the value 8, algebraically speaking, is 3 more than 5. So I'm going to write 1/n plus 3. So again, we arbitrarily stopped at 5, and 5 is related to 8, algebraically speaking, as n plus 3, where this is our n, and to get from 5 to 8, you're adding 3. So that's why we're writing n plus 3. Now we also have this term right here. So what I'm going to do for that is it's going to be -1 over, and again, to get from the n equals 5 to a 7, you're adding 2 to this number. So we write -1 over n plus 2. So I just want to make an arrow. This -1/8 corresponds to that, and this -1/7 corresponds to that term. And it's all according to n equals 5. So next we're going to consider the limit of partial sums. So that's the limit as n goes to infinity of s sub n, and the partial sum is going to be this entire expression. So when we take the limit of this expression, the limit of the constant 1/2 is just 1/2, plus the limit of this constant is 1/3, and then as n gets larger and larger, this fraction is going to go to 0, and this fraction is also going to go to 0. So when we add these fractions together, we end up getting 5/6. So therefore the series is convergent, and the original series equals 5/6. Alright guys, thanks so much for watching!